first thing is, what is a quantum state? So a quantum state space is just a system is a vector space. And we will explain this a little bit more later, but and we'll say, well, a qubit is a two-dimensional quantum space. Two-dimensional quantum state space. And actually, there's something about quantum mechanics that is probably different from the linear algebra that you've learned. Quantum mechanics, everything has complex numbers in it, so it's a complex vector space. So let's do examples. So the polarization of a photon, has, well, it basically has two distinguishable states, horizontal and vertical. And you can distinguish them by using a pair of Polaroid sunglasses. And the horizontal ones go through and the vertical ones go not, or do not, or vice versa, depending on which way you rotate your glasses. So spin of 1/2 spin particle is, the quantum states are up and down, or these are the basis states of the quantum state space. And harmonic oscillator zero, 1, 2, 3. Harmonic oscillator can be in a state corresponding to any natural number. And we won't be doing harmonic oscillators in this class, but if you've had any quantum mechanics, you've seen this. And so I will try to explain what this means a little bit later. So what now? So let's do an example of a four-dimensional state space. And let's call the basis vectors 0, 1, 2, 3. Okay. So I've been using this funny notation without explaining it, so now I get to explain it. V is a column vector. And a column vector will have 4 coordinates, so it will look like V0, V1, V2, V3. Okay. Okay, so a quantum state is a unit vector in a quantum state space. So associated to a quantum system is a quantum state space. So for example, associated to a spin 1/2 particle is a two-dimensional state space. And the state of a spin 1/2 particle can be any complex unit vector in the quantum state space. For example, V might be 0.5, 0.5, 0.7i, 0.1, which, if you sum the squares of these, you get 1, so it's a unit vector. And this funny-looking thing is called a ket. So this is Dirac notation, and it can be very useful. I hope to show you a calculation in which it's useful later today. But so this is a column vector. There's a corresponding row vector, which is called the bra, is equal to V transpose, or V conjugate transpose. So in this case, it is equal to 0.5, 0.5 minus 0.7i, 0.1. And why do these two things have these very funny names? Well, a bracket is equal to V is equal to, well, because V is a unit vector, and we're multiplying it by its conjugate transpose, you always get 1 if you have a quantum state, and WV is equal to, well, in math notation, I guess it would be W complex conjugate transpose V. And this is an inner product.